Today's lecture we will be talking on Fourier series, a continuation of our lecture, and we will go back to recall when we started Fourier series. We have already defined the definition and the Fourier series in our first lectures and first two material. But today we want to look at the even and odd function half-range Fourier series, and then we look at a Fourier series that is not within at any other range. So far we have been looking at a range of minus pi to pi and with a period of 2 pi. Just to cast your mind back, even function is when you have y is equals to f of s. We'll say the function is even if f of minus s is equals to f of s for all values of s. There's one thing you are going to see in the graph of an even function is symmetrical about its y-axis. That's what we call a mirror image. It repeats itself. The mirror image is symmetrical. Example of an even function is your y is equals to s squared and cos x. Now, odd function is a function where you have y is equals to f of s. The function is said to be odd if f of minus s is equals to minus f of s for all values of s. And the graph of the odd function is symmetrical about the origin. Examples, you have y is equals to s to the power of 3 and sine x is an example of odd function. There are other functions that are either odd nor even, and we have done that similar thing in advanced algebra. Now, Fourier series, Fourier cosine and Fourier sine series. We already know that the function, when the function is an even function, we'll say that example of that function is cos. So you are going to see that the Fourier series of an even function f of s having the period of 2 pi contain cosine term only. That means when the Fourier cosine series function an even periodic is an even periodic function that contain cosine term only. It does not contain any sine term. It may contain constant term. In my last class, I've given you the definition of a Fourier series. Now, when you look at that definition, you know the definition runs from 1 to infinity. Here you have plus b sine nx. But since you now have a Fourier sine series, there's no term of sine. So that's why you have this. The constant term where you have a is equals to 0 is you have 1 over pi, 1 over 2 pi, an integral minus 2, an integral boundary of minus pi to pi f of s ds. Now, because it's symmetry, due to symmetry, we have a naught to be 1 over pi. It's from the integral from 0 runs to pi. Take note of that for a naught. Now for an, you have 1 over pi, the integral from minus pi to pi f of s cos n s ds. I know that because due to symmetry, we have 2 over pi and as the integral from 0 to pi f of s cos n. That's for Fourier cosine series. Now for Fourier sine series, we already know that Odd periodic function, example of them is sine. And we know that sine function is an example of the odd periodic function. So the Fourier sine series has only the term of sine only. That's why you have this. And it does not contain any constant term. Does not contain no sine term. You can't see any of cosine term rather. So that's why there's no, you have bn, and here you have minus, no, you have 1 over pi, as the integral runs from minus pi to pi f of s sine n. As you look at symmetry on this, you have that this is the same as this, as 2 over pi, the integral from 0 to pi f of s sine s. Now I want to use the formula in A and B to now approach some problem. Now determine the Fourier series for the periodic function. This is the periodic function f of s, and it has a period of 2 pi. And as you look at this periodic function, we want to find the Fourier series. When you look at the wave, let's see a diagram. For this diagram, I need to stress this to you that sometimes in the exam, you may not be given the diagram, but your ability to look at it from your knowledge of, you have done elementary algebra, and you should be able to plot a graph. And you can see here from minus pi to 2 to, let me go back to my boundary, minus pi to minus 2 pi. I think I have 3, yes. So minus pi to minus 2 pi, I have this. Now, from pi, from minus pi to minus 2 pi to pi, you see it? I have 2. From minus pi to minus pi, that's minus 2. I think I can go up, but I cannot. So from minus pi over 2 to 2 pi, I have f of s is 2. And from pi over 2 to pi, f of s is minus 2. That's what you can see in the diagram. You can see from here that this is symmetric about the y-axis. And since y-axis, when I mean f of s, that's what I'm talking. So go back to what I started. If a function is symmetrical about the f of s, it means that that function is an even function. And when a function is an even function, it has only cosine terms. So instead of wasting your time writing all the formula, you just know that this Fourier series is contain contain cosine terms. So this will be your formula. There's no sine term. Now go back to your formula. You have this. You want to get a naught 1 over pi. That's the formula I've said due to symmetry. Now you now want to substitute. Your pi runs from 0 to pi. From your diagram, you have 0 to pi and pi to 2. So from pi to 2, f of s is 2. From let me just go back to, I think I can see, yes. From 0 to pi, f of s is 2. From half, that's half of pi to pi, f of s is minus 2. So that's why I have this 2 and this. But know that your interval is from 0, to pi. So what you just do is to differentiate. When you differentiate, you take the boundary. Here you are going to have 0. Now for a and see the same way, you now have 2 over pi integral from 0 to pi f of s. Already you know from 0 to pi is 2 cos ns ds. From pi to 2 is, from pi the integral interval from pi over 2 to pi is minus 2. So now what we do is to integrate this, you have this, integrate this, you take the boundary. So you are going to have this and this. Now, you are going to see something here that you can as well look at this and this. When you add it, you have this. So you are going to have 8 over pi n bracket open sine n pi over 2 bracket close. Now, this function you now have. Now, we want to see when n is even function like 2, 4, 6. This your function here will become 0. Because when you put, assuming you put 2 here, 2 will cancel this, you have pi. Sine 180 is 0, so everything here is 0. So when you put an even function, when n is even, your an is 0. Now, when you have odd function from the interval now, the odd function from 1, 5, as you put it here, you have this. From 3, 7, and 11, you are going to have minus. You can do that from your elementary trigonometry. Now let's come to this is what you are going to get. Your A1 will be this, A3 will be that. Then you go back to your formula, which you use, formula, this formula. You now substitute all these values. Your A naught is 0. Is it not? Your A naught is, what do we have in A naught? A naught is what? Did I say 0? Yes, A naught is 0. So that means I have A naught to be 0. So then when I substitute all this, there's something common here, that is 8 over pi. So I bring it out. So that's why you have this. In the same way, if you have this problem, problem 2 in the Fourier series of problem 1, let S. Now, when you look at the Fourier series of problem 1 we just did, f of s, this is the series we got. This is the Fourier series, f of s, 8 over pi into cos s. This is series. That's why you say a Fourier series. This is series. And now, in this Fourier series, you are asked to let s be equal to 0. Determine a series for pi over 4. So what you do here is this series, f of s is this. Now, if f of s is equal to 2, and is my f of s is equal to 2 from my question, go back to my question. My f of s is 2 within this. F of s is 2. So then I'm going to have my s is 0 from what you are giving. This let s be 0. So my f of s will be 2. Then my s will be 0. I substitute 0 here. 0. Everything will be cos 0, cos 0. You know, from your elementary knowledge of algebra and metric, cos 0 is 1. You are going to have 1 like that. Now, what you get here, this just simply means this will go there. It's like I divide both sides by pi, I will have 2 pi. I divide both sides by 8, I will have 2 pi over 8. So already I'm looking for deduce the series for pi over 4. So 2 cancel it. This is the series for pi over 4. Still the same pattern, but then this one is a little bit. This one you are given the diagram and you are asked to obtain the Fourier series for the square wave. This is the diagram, and you have here, from here you can see that the function is an odd function, because you can see that it's symmetrical about its origin. When you look at this function, within the interval of pi and your pi minus pi and pi, And within the interval of this, you can see that this function is symmetrical about about its origin. Look at like this, like this, this. So we can say it's symmetrical about its origin. Now, f of s we now if a function is symmetrical about the origin, we already know that that function is it comes to our mind that that's example of a sine function. That function is odd. So look at this. The function is defined by this f of s. F of s is minus 2 between the interval of 0, the interval of pi 1, from minus pi to 0. Your s there is minus 2. Y from 0 to pi, your f of s is 2. So now already you know that this function is an example of a Fourier series of Fourier sine series. So you know that there will not be any constant term. So we have Bn. From the formula you have 2 over pi. The integral from 0 to pi f of s sine n ds. Now, here is your f of s. Your f of s within this interval 0 to pi is 2. So you have 2. The interval 0 to pi, you have 2. So this minus 2 is not within the interval of this integral. So when you integrate this, you are going to have this. And you now have this function. When you substitute, and when n is even, all this thing here will be n will be 0. But when n is odd, 1, 3, 5, you are going to have this. You do that on your own. Then, having gotten this, go back to this formula of this. You now substitute this. So that's how we got the Fourier series for this function. Now, let me just look at that before going to another aspect. That is, I think it's similar, but let me just see. Determine the Fourier series for the function f of theta is equal to theta square in the range of minus pi is between minus pi, theta is between minus pi and pi, and the function has a period of 2 pi. So as you look at the function, f of theta is equals to, can we see the function? Okay. F of theta, you see, you are being defined from here to here. You are going to see that this function we are looking at is an even function because it's symmetrical about the y-axis. It's symmetrical about the y-axis. Now, if you look at this function like this, you see that this is the interval you are looking from minus pi to pi. You are going to see that from an extension of this tells you something that the function is this. So this like this. So it's telling you that the function is symmetrical about f of theta. So that tells you the function is an even function. An example of such an even function tells you that that is a Fourier cosine series. So you have this, because there will not be any term of sine. This will be the formula you want to use. Now, because it's a Fourier series of cosines, then you are going to have a constant term and you are also going to have an. So go back to your formula for this. You have 1 over pi from 0 to pi f or theta d theta. So from the question, theta from 0 to pi, you can see from this diagram, from 0 to pi, you have theta square. From 0 to pi, you have theta square. So my f of theta will be theta square. So when I integrate, I have this. Now let me be a little bit faster. When you have, I've gotten my a naught, so I come to my a n 2 over pi, use the formula from 0 to pi. Now from 0 to pi, you know that f of theta is pi squared. When you integrate this, using integration by part, you have this. When you substitute within the boundary 0 and pi, you are going to have this. Now you now have your your an to be this. Now when your n is odd, already you know what is odd function, like 1, like 3 and 5. These are what you are going to get. But when your n is even, you have 2, 4 is what you are going to get. You are substituting n in this. So this is what you have. So your Fourier series will now be this. I don't need to explain so much on that, but you go back to this and substitute it. I think that's for that. Now, let me go to another aspect, which that one is something you can practice on your own. This is a similar thing on what I did in the other example, just for you to. Now, I want to go to half range Fourier series. So far, we have defined a function over from the interval from 0 to pi. And we have looked at, now we want to see that we can as well look at half range. We have defined from 0 to 2 pi. Now, if we now define a function in a range from 0 to pi, so that's the picture of what we call half range Fourier series in terms of cosine term or in sine term. There are other things there you can read on your own, but let me just go to problem. So if I have a function like this, which is symmetrical at f of s, this will be my Fourier series. That's half range cosine series. Already you know that cosine series is an example of even function. Now you are going to define the boundary between 0 and pi. You see that my interval is between 0 and pi. So I'm going to have a naught to be 1 over pi. This is my formula. An to be this from 0 to pi. Now the same way I look at the half range sine series. So this will be my, here when I look at this series, I know that this series, if I is a odd function that is symmetrical about the origin. Look at it, it's symmetrical about the origin. About the origin. That's why you have extension on dot line. And when a function is symmetrical about the origin, what comes to our mind is an odd function, odd periodic function. So an example of that is your Fourier sine, but now we're looking at half range Fourier series. So this will be my formula for this. Now let me see one or two problem. Let's see problem 8. Now determine the half range Fourier cosine series. We represent the function f of s is equal to 3s in the range of between 0, s is between 0 and pi. Now, because you are already told that this is a formula, we have done that. I've explained that just now. I've shown you the formula. So this is the formula. Now, what you just need to do is to recall this formula. F of s is a naught plus the summation from n to infinity a n cos nx. Now, what you now looked at is that your f of s is this. You want to get your a naught. You are substituting this f of s. You have your interval is between 0 and pi. But you look at the other one we have been looking is between 0 and 2 pi, periodic or 2 pi. Well, now it's between 0 and pi. Your f of s is 3. So when you integrate, you have this. The same vein, when you have this for a or this formula, f of s is 3. When you integrate this, you know you have to integrate integration by part. You have this. And when you substitute your boundary from 0 and pi, from 0 to pi, you have this. Now, having gotten this, you have to now see where n is evil. Put evil here, what will be your function? It will be 0. When n is odd, when we say odd function, like you say 1, 3, 5, like that, this function will give you this. When n is odd, you will have this. And so when you now have n1 this, n3 like that, because the function when n is odd. But when n is evil is when n is 0, an is 0. So already you now have to substitute. You know your a0, your a0. I think we have a0. Yes, we have 3 pi over 2. So you substitute it. And that's how you got this Fourier series. So that's an example of using half range Fourier series. Now, for the same way with sine, we have done cos. So f of s is equals to 3x in terms of the range of s is in terms of the range of 0 and pi. Now, go back. We are already told this Fourier sine series. You know that there will not be any term of cos. So you now have this your formula. F of s is this because there is no a naught. So your f of s is your bn is 2 over pi, the integral, this formula. Now you know your boundary of your integral from 0 to pi. Your f of s is 3s. So when you do integration by part, you are going to have that. And when you substitute your interval, you have this. Now when your n is odd, when you put odd here, your odd function, you are going to have 1. I say 1, you are going to have 6 over n. Because all this function when it's odd will be 1. So when you have b1, your n is 1, you have 6. When your n is 3, because it's odd function, you have this. Now, when the function is evil, everything here will becomes minus 6 over n. So when you have evil, you have 2, you have 4, you have 6, so on. And you know an infinite series, so it continues, so on. So now your Fourier series will now be, you substitute this function. I say all these values into that. That's how you get the Fourier series. So let me not waste much time. It's a similar examples. I've just explained it to do for you. A summary for this part. When you are looking at an interval, so far you have looked at the interval between 0 and 2 pi. So half of that interval is between 0 and pi. So such range is what we call half range Fourier series. We have also looked at the evil function and odd function. And we say that a Fourier odd function, when it's odd, we say that the Fourier series has sine only. And when it's evil, the Fourier series has cosine term only, and it has also a constant term. Now, before I will round up the lecture, I want to take another part that has to do with, in this course, we have looked at the range of 2 pi from 0 to pi. Our periodic has been from 2 pi. And now we want to see that What can we look at the advantage of Fourier series is that we can look at the range when the function is periodic, when the function is not periodic, and we can also look at a range that is outside the period. So that was one of the beautiful applications in Fourier series above other series. Now we are going to look at Fourier series over any range. As I've said, we have moved so far as between 2 to pi, 0 to pi, half sine. And now we want to now see if we already know a periodic function, if we now try to look at the function that is, we are changing the function from 2 pi to a function that is having L. It is not difficult since we have already have a concept of change of subject formula. So what do we need to do is that we are going to express the function f of s in terms of function of u. So what I'm saying is that I'm going to say my s to be equal to my u to be 2 pi x over L. So if my u is 2 pi x over L, so what I'm just saying that the range of, if I'm using u equals to 2 pi x over L, so when s is minus, my s will be minus L over 2 when my u is pi, minus pi. If you go back to the first formula we used in Fourier series, we looked at the range of minus pi to pi, and we said that the period is 2 pi. So now we are now looking at the range. We are now seeing that a function, we are using a new variable u, which will now say f of s will now be in a function of f of u, as if we are replacing s by u. So we now say u in the function. So u will become 2 pi s. When I say replace, we are replacing f of s by f of u. Does not mean we are displacing s. So you are going to see here that when we have this function, so when I make, so that's why I'm saying I'm not displacing here now. I have u is equals to 2 pi x over L. So if I want to make s the subject of formula, I'm going to have, I will have u, I will have Lu over 2 pi. So what this is saying is that when u is minus pi, s will be minus L pi. That's how we got this interval. And when u is equal to plus pi, s will become L over 2. So you are taking a new range of the function of s. When I want to define a Fourier series for f of s in a range of minus L over 2 less than equals to, or when I say from minus pi L over 2 to L over 2. So those are just the concepts you can get some. So if that's what I did here, this become f of u. So this function, go back to the concept of the Fourier series. So in place of s, I'm going to say f of u. So I will now replace my function of s by u. So I'm going to have this, the interval from this, I'll have this, I'll have this. Now, I want to now change, because I'm using u, I've already introduced u. I'm using u to be, I'm using u to say that u is equals to 2 pi x over L. So if I differentiate u with respect to s, I'm going to have 2 pi over L du over ds, 2 pi over L. So if I make du the subject of formula, I'm going to have 2 pi over L du. So in my integral, the limit of my integral, which I know will not change, will now be minus pi over 2 to plus, I say minus L over 2 to plus L over 2 instead of this minus pi. So what I'm coming to this interval, I mean integral limit, that instead of pi, I'm going to put L over 2. Instead of minus pi, I'm going to put minus L over 2. So automatically, my f of s will become this. It's not something strange I've done. So in place, I have this. I'll have this. So I just brought in 2 pi L. No, I differentiated, so I'll have this. That will be in this range. Now finally, I'm going to put, that's what I'll be using. From this range, my integral will now be a naught 1 over pi. 1 over L. Sorry, I'm still using the middle. It's no longer using pi, it's 1 over L. Integral minus will go from minus L over 2 to L over 12 of L. My AN will be 2 over pi. 2 over L. The integral runs from minus L. The limit of the integral is minus L over 2 to L over 2 f of s. You see that my cos will become 2 pi ns over L dx. So the same way with pi. So what we have done is that the limit of the integral we maybe replace with the interval of L2, such as, okay, I think when we solve problem, I would explain that. We can as well replace this integral from the range from 0 to pi. We'll do that when we are solving. I think I will explain that. Now see this example. Problem 1, find the voltage from a square wave generator is of this form, f of t, and the period, it has a period of 8 milliseconds. And so that's the period of this. Find the Fourier series for this periodic function. Now look at you already know you have Vt. So your formula will become, in place of S, you are going to have T. That's your Fourier series of this form. Now already you have been given, if you understand the diagram very well, this is telling you that from minus 4 to t, you have 0. And from 0 to t, you have 4. And then you know the period there is 8. So now come to this formula we are going to use. Now what we are saying here is that your L is 8. And then when you put 8 here, you are going to have this. What is your f of t? Now you have this. What is your f of t? When the interval from minus 4 to 0 is, f of t is 0. From 0 to 4, f of t is 10. So that's how you got this. You have done integrations in somehow we do this equation. That should not be a problem. Just a sum. So now, when you have this for an, this is the formula you want to use. Your L is 8. So when you substitute, you are going to have 2 over 8. That's 1 over 4. So your interval is from minus 4 to 4. So from minus 4 to 0, f of t is 0. From 0 to 4, f of t is 10. So when you integrate, automatically you know that you're integrating this gives you 0. But when you integrate this, you have this. And when you substitute, you will get this. So now, automatically when you have your an, for n is equal to 1, 2, 3, your an will be 0. You have this, and for n is equal to 1, 2, 3 to be 0. Your Bn, this is the formula you are using. When you have, you know your L already, so you have this. You know the interval, so you are going to have the integral interval of this. So when you differentiate, already you know that this 0, when you differentiate this, you are going to have this. And then when you substitute your value, you are going to have this. So now, from the value you got, this value, when n is equal to, when n is even, you are going to have Bn to be 0. But when n is odd, you have this. When B1, you have this. B3, you have this. B5, and so on and so forth. So then your Fourier series, you already knows your A naught, and as well as your Bn is 0, but you know your your An is 0. So you substitute this into this Fourier series expansion. I need to clear that to you. When your Bn is 0, so everything here is 0. I think that's what I want to explain. Is there any other one I need to? The other aspect is, okay, this obtain the Fourier series for this function. This function is periodic outside the range of 4. What it's telling you is that this function where you have L is equal to 4, but it's telling you that the function is periodic outside this range of 4. And so, looking at this function, can we look at the diagram? In this diagram, I can say that between minus 2 to 2, my function is also periodic. But outside this range is also still periodic. So, but when I look at this function, I can say that it is symmetric about its f of s. So what comes to my mind is when the function is symmetric about f of s, that function is odd. Is odd is if that function is even function rather. So when it's even function, then that comes to your mind that I'm going to have no sine term, no sine term. So this is the formula I'm going to use. There's no sine term because the function is even function. So what I will do is that my A naught, I can get my A naught. So my interval here is 4. So I'm going to have this. And then my interval, my period is 4. Look at my range is from minus, sorry, my range is from, my range, when I substitute 4 here, I'm going to have this. So when I integrate, so look at the integral from minus, can I go to the question? From minus 2, so you are taking the range from minus 2 to 2. So from minus 2 to minus 1, the interval, the f of s, is it f of s that is there? Yes. So let me just stay with this. From this to this is 0. From this to this is 5. From this to this is 0. So that's how you got this. That's how you got this. So automatically you are going to know this is 0, this is 0. When you integrate this, you have this. Now when you look at this, an, you have 2 over pi. And I said 2 over L rather. This is the formula. You already know your L, so when you substitute this, you have this. Now, the same way you look at it, what is your f of x? You are taking the range from minus, your integral limit from minus 2 to 2. So, from minus integral from minus 2 to 1, you have this. Integral of this function from minus 1 to 1, you have this. From 1 to 2, you have this. You know this will give you 0. So when you integrate this, you will have this. And then you take the interval, you are going to have this. So you now have to substitute. When n is even, all this will give you 0. So when n is odd, 1, 3, 5, you have this. So take your time to look at some of these things because we may not be able to explain them in detail, but you know how to use it. When it's odd, there is say n is 1, you substitute it. This is what I'm talking about. So this will give you the Fourier series for this. I haven't gotten the value, you substitute it. I don't think there's anything so special from what I'll be explaining. But maybe before I round up, let me go to. There are some other you practice them. There are some problems there you do it. I've decided not to give you my assignment because I have many problems there in the test, the material I'm giving you. So practice them or you're not. At the end of the lecture, I will give you an assignment for you to submit, what I will use as part of my assessment. Now, let's look at a half-range Fourier series for the function defined over the range of L. Now, we have done the one of the function. Now, if you go back to, we now want to substitute that we are putting u to be pi over SL. So now we are taking the range from 0 to pi. So that will be that when u is 0, we are going to have the range that is that's u, my L will be when u is 0 and when my pi, okay, when my pi is, I will have L and I will have 0. You see that when I, so this is just half range, okay, half range Fourier series. So I'm taking the range from 0 to pi. And then because I'm going back to my formula, so but here I'm now substituting the other formula I used 2 pi s, but here I'm using pi s over L. So when I substitute this, so my range is from 0 to pi. My range here is from 0 to pi. Let us go back to this one I did when I started. See the range I got this, the range of this, the range of this. So the same way, this one here, we took a range where we say u is equals to 2 pi over 2 pi s over pi. So now we were able to use for L, that's the period, we have minus pi, minus L2 to plus L2. But now you are now going to look at a range of 0 to L. So just go back to that example and see, because there's no way for us to prove how we got this, but it's a similar way to that. So your interval here will now be what this is saying, that when u is 0, from 0 to pi, you are now going to have 0 to L. That's what it's saying. So I think these are the formula you need to take to heart for half range cosine series in the range of 0 to L. This also the formula from 0 to L for half-range sine series. This one. Now, let me just look at one example. If you have a Fourier series, okay, determine the half-range Fourier cosine series for the function f of s is s in terms of this range 0 to 2. We will have to stretch the function within and outside the range. So what you just need to do is that this is the function, but we are giving from 0 to what? Okay, 0 to 2. That's what you want to look at, from 0 to 2. But you are going to see if you stretch it outside this range, it will be like this, like this. So this to this. So what this is telling you, this. So the function is an example of the function. From the broken line, we can see that it is symmetric about f of s. Symmetric about f of s. See if we can see my cursor. So it's symmetric about f of s. And we already know that the function is a Fourier, it's a half-range Fourier cosine series. Without wasting more time, I already know the formula to be f of s, to be this. A naught, the summation as n runs from 1 to infinity, an cos n pi s over L. So my A naught is 1 over L integral from 0, the limit from 0 to L, f of s df. Now you need to know what is your f of s is x. What is your limit? What's the L? Your range of your interval is between 0 and 1. So your L will be 2. Just from here to here is 2. Here to here is 2. So your range is 2. That's your L is 2. So when you integrate this, you have this. For an, you have this. Your f of s is s. So when you do the integration for this, you are going to have this function. And you are going to have integration by parts. You have this. So go back to do more about your elementary integration, and when you substitute this, you will have this. So eventually you will get this. Now I haven't gotten this. When your n is even numbers. When it's even number, everything here will become like you have 1. 1 minus 1 will be 0. So everything here will be 0. But when it's odd, you have 1, you have 3, you have 5, you are going to see that this is what you will get. So your half-range cosine series for this interval from 0 to 2 will now be this. So what we have looked at is a similar thing. Let me not just repeat myself, but I think it's a similar thing, just that here we are not dealing with sine. So let me just recall to you that you can look at a Fourier series with over any range. It may not necessarily has to be 2 pi. So far, since we started the course, we have been looking at 2 pi. In fact, our definition of Fourier series was defined on a period of 2 pi, where we looked at a range of minus pi to pi. But now we went further to say that it may not necessarily be on that range of 2 pi. It can be in the range of L, and we can as well introduce a new variable u, which will be a function of u equals to 2 pi s. I mean, u will be 2 pi s over L. So you have to go back to all these materials, go through them, and if you have any questions, I have not been able to have Zoom lectures, but you can use the WhatsApp platform. If there are things you are not clear about, you can ask and I can explain them. Because within the time for the lecture, there's no way we'll be able to explain anything. I may play everything. So, but you go through the materials and the lectures. If you have questions, you are free to ask on your social platform, and so that we can respond. I have just one aspect to look at before I round up the course, and that will be partial differential equation. Partial differential equation. I will not go so deep in that, just an introductory aspect. So you will get the link to this material and the lecture.